Welcome to this self-led lesson on model performance metrics in production machine learning systems. Today, we're diving into one of the most critical aspects of deploying and maintaining machine learning models in real-world environments: how to measure, monitor, and maintain model performance over time. As models move from development into production, they face dynamic data, evolving user behavior, and shifting business requirements. Without a robust monitoring strategy, even the most accurate models can degrade silently, leading to poor user experiences and costly business outcomes. This workshop is designed to equip you with practical, actionable knowledge to track performance metrics, detect issues early, and respond effectively. We'll explore foundational metrics like accuracy, precision, and recall, and go beyond them to understand drift, degradation, and threshold setting. You'll also get hands-on experience building a monitoring dashboard that brings all these concepts together. By the end of this session, you'll be empowered to implement a comprehensive monitoring system that ensures your models stay reliable, relevant, and aligned with business goals. Let's take a look at what we'll be covering in this lesson. Our goal is to build a strong foundation in understanding and applying model performance metrics in production environments. We'll start by exploring the fundamental metrics: accuracy, precision, and recall. These are the building blocks of model evaluation, and we'll discuss not just how they're calculated, but when each is most appropriate depending on your use case. Next, we'll dive into model drift and degradation. This is where things get real in production. Models don't operate in a vacuum. They're exposed to changing data, evolving user behavior, and shifting business contexts. We'll examine the different types of drift, what causes them, and how to detect them before they impact performance. Then we'll move into setting performance thresholds. It's not enough to just monitor metrics. You need to know what values are acceptable and when to trigger alerts. We'll cover both quantitative and qualitative approaches to defining these thresholds, ensuring they're aligned with business impact and user experience. Finally, we'll bring it all together in a hands-on exercise where you'll build a monitoring dashboard. This interactive portion will help you apply everything you've learned in a practical, real-world scenario. By the end of this workshop, you'll be equipped with the skills to implement a comprehensive monitoring strategy that keeps your models performing reliably in production. To effectively evaluate machine learning models, especially in production, we need to start with a solid understanding of the core performance metrics. These metrics help us quantify how well our models are performing and guide us in making informed decisions about improvements, retraining, or deployment strategies. Let's begin with accuracy. Accuracy measures the proportion of all predictions, both positive and negative, that are correct. It's calculated using the formula shown, where TP stands for true positives, TN for true negatives, FP for false positives, and FN for false negatives. Accuracy is intuitive and useful, but it can be misleading in cases of class imbalance. Next, we have precision, which tells us how many of the predicted positive cases were actually correct. Precision is especially important when the cost of false positives is high. Think of scenarios like spam detection or medical diagnoses. Then there's recall, which measures how many of the actual positive cases were correctly identified by the model. ADAS recall becomes critical when missing a positive case is costly, such as in fraud detection or disease screening. Finally, we have the F1 score, which is the harmonic mean of precision and recall. It balances the trade-off between the two. The F1 score is particularly useful when you need a single metric that captures both false positives and false negatives. Understanding these metrics is the first step toward building reliable, production-ready models. Each one offers a different lens through which to evaluate performance, and choosing the right one depends on your specific use case and business priorities. Now that we've covered the core performance metrics, accuracy, precision, and recall, it's important to understand when to use each one. Not all metrics are created equal, and choosing the right one depends heavily on your specific use case and the consequences of different types of errors. Let's start with accuracy. Accuracy is a great metric when your classes are balanced and the cost of false positives and false negatives is roughly the same. For example, in a general image classification task where all categories are equally important, accuracy gives you a good overall sense of how well your model is performing. But beware, accuracy can be misleading in imbalanced datasets, where one class dominates the others. Next, we have precision. Precision becomes critical when false positives are costly. You want to be confident that when your model predicts a positive, it's actually correct. A classic example is spam detection. If your model incorrectly flags legitimate emails as spam, it can lead to missed communications and frustrated users. In this case, high precision ensures that only true spam gets filtered out. On the other hand, recall is the metric to focus on when false negatives are more dangerous. You want to catch as many positive instances as possible, even if it means tolerating some false positives. A good example is fraud detection. Missing a fraudulent transaction can be far more damaging than investigating a few legitimate ones. High recall ensures that you're catching as many fraud cases as possible. Understanding the trade-offs between these metrics is essential for aligning your model's behavior with business goals and user expectations. In many cases, you'll need to balance precision and recall, which is where the F1 score comes in, but we'll explore that more in context later. While accuracy, precision, and recall are essential for binary classification tasks, real-world machine learning often involves more complex scenarios. That's why it's important to understand how to evaluate models beyond simple yes or no predictions. Let's start with multi-class classification. When your model predicts one of several categories, like identifying the type of object in an image, you need metrics that account for performance across all classes. There are three common approaches. Macro averaging treats all classes equally. It calculates metrics for each class independently and then averages them. This is useful when you care about performance across all categories, regardless of how frequently they appear. Microaveraging aggregates the contributions of all classes before calculating metrics. This approach favors classes with more examples and is helpful when overall performance is more important than per-class fairness. Weighted averaging strikes a balance by averaging metrics for each class, weighted by how often each class appears. This is ideal when you want to reflect the real-world distribution of your data while still accounting for individual class performance. Now let's talk about regression tasks, where the model predicts continuous values rather than categories. Here, we use metrics like mean absolute error, MAE, which calculates the average of the absolute differences between predicted and actual values. It gives a straightforward sense of how far off predictions are on average. Root means square error, RMSE, which squares the differences before averaging and then takes the square root. This penalizes larger errors more heavily, making it useful when big mistakes are especially costly. Choosing the right metric depends on your model type and business context. Whether you're classifying, ranking, or predicting numeric values, understanding these metrics ensures you're evaluating performance in a way that truly reflects your goals. As machine learning models operate in production, one of the most common and challenging issues they face is model drift. Drift refers to changes in the data or environment that cause a model's performance to degrade over time. Understanding the types of drift is essential for maintaining model reliability and ensuring continued alignment with business goals. First, we have concept drift. This occurs when the relationship between input features and the target variable changes. For example, imagine a recommendation system that relies on customer preferences. If a major economic event shifts consumer behavior, the model's assumptions about what drives purchases may no longer hold true. Even though the input data looks similar, the underlying patterns have changed. Next is data drift, which refers to changes in the statistical properties of the input data itself. A good example is a computer vision model trained on low-resolution images. If your user base starts uploading higher quality images, the pixel distributions shift, and the model may struggle to interpret the new inputs correctly. Finally, we have upstream data changes. These are changes in data sources, schemas, or pre-processing steps that feed into your model. For instance, if a third-party API changes its response format or alters how it calculates a feature, your model might receive data it wasn't trained to handle, leading to unexpected behavior. Drift often happens gradually, making it easy to overlook until performance drops significantly. That's why early detection and proactive monitoring are critical. By understanding the different types of drift, You can design systems that catch these changes before they impact users or business outcomes. Once we understand what model drift is, the next step is learning how to detect and measure it effectively. Drift can be subtle and gradual, so relying on intuition or manual checks isn't enough. We need statistical tools and structured monitoring approaches to catch it early and respond appropriately. Let's begin with statistical tests. One powerful method is the Kolmogorov-Smirnov test, which compares the cumulative distributions of two datasets and measures the maximum distance between them. It's particularly useful for identifying shifts in continuous variables. Another tool is the Population Stability Index, or PSI. This quantifies changes in variable distributions over time, and a PSI value greater than 0.25 typically signals a significant shift. We also have Jensen-Shannon divergence, which measures the similarity between probability distributions, ideal for comparing categorical or probabilistic outputs. Beyond statistics, we need robust monitoring strategies. A window-based approach compares data from different time periods, say, this week's data versus the training set. This helps identify short-term anomalies. Sequential analysis, on the other hand, monitors data as it arrives and triggers alerts when cumulative changes exceed a threshold. It's great for real-time systems. And then there's shadow deployment, where a new model runs alongside the current one without affecting users. By comparing their predictions, you can assess performance before a full rollout. Here's a key insight. Statistical significance doesn't always mean practical significance. Not every detected drift requires immediate action. That's why it's crucial to combine statistical methods with domain knowledge. Understanding the business context helps you decide whether a change is meaningful or just noise.
Now that we've covered how to detect drift, let's talk about how to implement drift detection in practice. This is where theory meets engineering, and where a well-designed monitoring system can make all the difference in maintaining model performance. The first step is to select the features you want to monitor. These should include key input features that drive model predictions, the model's outputs themselves, and even intermediate representations if your architecture allows it. Monitoring these layers gives you visibility into where drift might be occurring, whether it's in the data, the model's logic, or its predictions. Next, you need to establish baselines. These come from your training and validation datasets. You'll want to capture the distributions of your features, the performance metrics during validation, and the expected ranges of variation. These baselines serve as your reference point for detecting change. Then, it's time to set alert thresholds. This involves defining statistical significance levels, like a PSI value above 0.25, as well as thresholds based on business impact. For example, a small change in a feature might be statistically significant but irrelevant to business outcomes. You can also set rate of change triggers to catch rapid shifts that might indicate a serious issue. Finally, you'll want to automate your response mechanisms. This includes sending alert notifications when thresholds are breached, triggering model retraining workflows, and implementing fallback systems to maintain service continuity. Automation ensures that you can respond quickly and consistently, even when issues arise outside of business hours. The most effective drift detection systems combine multiple monitoring approaches, each tailored to different types of features and potential issues. By layering statistical tools with business logic and automation, you create a resilient framework that keeps your models performing reliably in production. To bring these concepts to life, let's look at two real-world case studies that highlight the critical importance of drift detection and monitoring in production environments. First, consider an e-commerce recommendation system used by a major online retailer. Over the course of just 2 weeks, they noticed a 15% drop in click-through rates on recommended products. At first glance, standard performance metrics like accuracy and precision showed minimal change, which made the issue hard to detect. But upon deeper investigation, they discovered that holiday shopping patterns had introduced temporary concept drift. The model was still functioning as designed, but the relationship between customer behavior and product preferences had shifted, If they had been monitoring feature distributions more closely, they could have caught the drift earlier and adjusted the model proactively. Now let's look at a fraud detection platform used by a financial services company. They began seeing a rise in false positives, legitimate transactions being flagged as fraudulent. Interestingly, recall remained high, meaning the model was still catching most fraud cases. But precision dropped significantly, leading to unnecessary investigations and customer friction. The root cause? New payment methods had introduced data drift, changing transaction patterns in ways the model wasn't trained to handle. Fortunately, early detection allowed the team to retrain the model on these new transaction types before the issue escalated. The key takeaway here is simple but powerful. Models that perform well during development can deteriorate rapidly in production. Continuous, multidimensional monitoring isn't a luxury, it's a necessity. By tracking not just performance metrics, but also input data and model behavior, you can catch issues early and maintain trust in your AI systems. Once you've identified the right metrics and established a monitoring system, the next critical step is to set appropriate performance thresholds. These thresholds define what acceptable performance looks like and help you determine when to take action. But setting them isn't just a technical exercise. It requires a thoughtful balance between statistical rigor and business context. Let's start with quantitative approaches. One method is using statistical confidence intervals based on validation data. For example, you might set a threshold that expects your model's F1 score to stay within a 95% confidence interval. Another approach is defining degradation tolerance, how much performance can drop before it becomes unacceptable. A common rule might be no more than a 5% decrease in F1 score from baseline. You can also use ROC curve analysis to adjust classification thresholds, helping you balance precision and recall based on your specific needs. But numbers alone aren't enough. You also need to consider qualitative factors. Start with a business impact assessment. How does a change in performance affect revenue, cost, or customer satisfaction? Then think about user experience. What error rates are tolerable from the user's perspective? Finally, don't forget regulatory requirements. In some industries, models must meet standards for fairness, transparency, or accuracy, and thresholds must reflect those obligations. One common mistake is setting arbitrary thresholds without considering context. For instance, a 1% drop in accuracy might seem minor, but in a high-volume mission-critical system, it could be catastrophic. Conversely, a 5% drop in a low-impact application might be perfectly acceptable. Ultimately, threshold setting is both a science and an art. It requires collaboration between data scientists, engineers, and business stakeholders to ensure that your monitoring system is not only technically sound, but also aligned with real-world priorities. To make threshold setting more strategic and scalable, it helps to use a performance threshold framework that considers both technical complexity and business impact. This framework allows you to categorize models and tailor your monitoring and response strategies accordingly. Let's break it down into 4 quadrants. In the bottom left quadrant, we have models that are non-critical and low complexity. These are simple models with minimal business impact. Think of internal tools or low-risk automation. For these, lightweight monitoring and relaxed thresholds are usually sufficient. Moving to the bottom right, we find critical but low-complexity models. These might be simple models that support high-impact functions, like a rule-based fraud filter in a financial system. Even though the model is technically simple, its business importance demands tighter thresholds and more frequent checks. In the top left quadrant, we have non-critical but high-complexity models. These could be experimental models or research prototypes. While they're technically sophisticated, their business impact is limited, so you can afford to be more flexible with thresholds and monitoring intensity. Finally, the top right quadrant is where things get serious: critical and high-complexity models. These are the backbone of your production systems, such as recommendation engines, credit scoring models, or real-time personalization algorithms. For these, you need rigorous monitoring, finely tuned thresholds, and automated response mechanisms. The key to success is cross-functional collaboration. ML engineers bring deep technical insight, while product managers understand business priorities. Together, they can define thresholds that are both technically sound and strategically aligned. Use this framework to guide your decisions and ensure that your monitoring efforts are proportional to the model's role in your organization. To ensure your machine learning models remain reliable and effective in production, you need more than just a few metrics. You need a comprehensive monitoring system. This system should cover multiple dimensions of model behavior, from the data flowing in to the predictions going out and everything in between. Let's start with input data monitoring. This involves tracking the distributions of key features, checking for missing values, validating schemas, and assessing overall data quality. If your input data starts to drift or degrade, your model's performance will follow. Catching these issues early helps prevent downstream problems. Next is model behavior monitoring. Here, you're looking at how the model is making decisions. Are the prediction distributions consistent? Are confidence scores within expected ranges? Are edge cases being handled appropriately? You can also include explainability metrics to ensure the model's reasoning remains transparent and trustworthy. Then we have performance monitoring. This is where traditional metrics like accuracy, precision, and recall come into play. But don't stop there. Track performance across different segments of your data, monitor changes in the confusion matrix, and correlate model metrics with business KPIs. This helps you understand not just how the model is performing, but how that performance translates into real-world impact. Finally, there's operational monitoring. This includes inference latency, resource utilization, error rates, and endpoint availability. These metrics ensure your model is not only accurate but also efficient and reliable from a systems perspective. A robust monitoring system integrates all these dimensions to provide complete visibility into model health. It enables proactive maintenance, faster troubleshooting, and more confident decision-making. In short, it's the foundation of trustworthy AI in production. Now it's time to put everything we've learned into practice. In this hands-on portion of the workshop, you'll build a starter model monitoring dashboard that brings together the key concepts of performance tracking, drift detection, and alerting. We'll begin by selecting key metrics. Choose 5 to 7 metrics that span across input data, model outputs, performance indicators, and operational health. These should be tailored to your specific model and use case. For example, you might track feature distributions, prediction confidence, F1 score, inference latency, and error rates. Next, you'll define thresholds for each metric. Use your training and validation data to establish baseline values and set alert thresholds based on business requirements. Think about what levels of change are acceptable and what should trigger an investigation or response. Then, you'll implement visualizations. Create time series plots to track metrics over time. Compare distributions between datasets, and highlight anomalies. These visualizations will help you quickly spot trends and outliers that could indicate drift or degradation. After that, you'll set up alerting mechanisms. Configure notifications for when thresholds are breached, and assign severity levels and escalation paths. This ensures that the right people are informed at the right time, and that issues are addressed promptly. Finally, you'll document response procedures. Create playbooks that outline how to investigate and resolve different types of performance issues. Whether it's retraining the model, adjusting thresholds, or rolling back a deployment, having a clear plan in place will save time and reduce risk. You'll be working with a template code base and a sample dataset to get started. By the end of this exercise, you'll have a functional dashboard that you can adapt and expand for your own production models. As we wrap up this workshop, let's revisit the key takeaways that will guide your journey toward building resilient, production-ready machine learning systems. First, remember that metrics must match your use case. There's no one-size-fits-all solution. The right performance metric depends on your business objectives and the specific costs associated with different types of errors. Whether it's precision for spam detection or recall for fraud prevention, your metrics should reflect what matters most to your users and stakeholders. Second, drift is inevitable. Every production model will experience some form of drift, whether it's concept drift, data drift, or upstream changes. The real question is whether you'll detect it before it impacts performance. Proactive monitoring is your best defense against silent degradation. Third, multidimensional monitoring is essential. Don't rely on a single metric or a single layer of observation. Track input data, model outputs, performance indicators, and operational health together. This holistic approach gives you complete visibility and helps you catch issues from multiple angles. Fourth, automate where possible, but keep humans in the loop. Automation helps you scale monitoring and respond quickly, but domain experts are still crucial for interpreting complex changes and making strategic decisions. The best systems combine machine efficiency with human judgment. Finally, for continued learning and implementation, be sure to access the workshop materials, code templates, and additional resources available at github.com AI for Prod Model Metrics Workshop. These tools will help you build and refine your monitoring systems with confidence. Thank you for participating, and here's to building smarter, more reliable AI in production.